or maybe we can just discuss like things that relates to our project in general. For example, what was the biggest challenge that you encountered in this work and how do you overcome it? So for example, take my project as an example, I'm interested in using metformin. So I'm using genetics to help infer the drug's effect. And one of the challenges with metformin itself is that the mechanism is not well understood and there are multiple pathways. So that makes it very, very difficult for us to really identify the relevant genetic variants to proxy the effect of metformin. But it's an interesting project because throughout time, you identify additional literature to help you refine the way how you design the study. So it's not always the same as how you originally proposed, because even within a year's time, there are a lot of advancement in the areas that I believe that we are all working on. So I think that's a challenge, but also I think that's part of the interesting thing that we work on, in research. So any other thoughts that other awardees would like to share?
Ryan, in sort of feeling your pain, for us, it's always about powering a study effectively, right? So we can do really cool things with one stem cell line, which, you know, back in the old days, which is just a couple of years ago, that was fine for publication and to sort of make a lot of claims. Now we're thinking about, you know, how many individuals do you need to look in, even if they're specialized individuals. And then from in vitro assays, how many can you actually, you know, run, you know, even with robotics or something of that nature, to sort of look to see if the effect is linked to genetics or is something that's actually real. So one of the ways that we're looking at it is something called cell villages, which is sort of a new thing. So I know you use cells and cell lines back in the day, and the whole concept is, instead of looking at these individual lines one at a time, we sort of put them all together, let them sort of grow together, and sort of look at the impacts there that we can deconvolute later using bioinformatics, so that you actually maybe look at things more on a, not on a population scale, but on a village scale. But it's hard. So powering these things is, I think, one of our biggest challenges.
Right. Yeah, I think that's the same issue, even if we're working on, say, population level studies, because my research mainly on the public health side, but in the past, we were talking about 1,000 people or a couple of thousand people would be enough. But now, for example, in one of the largest biobank, we're talking about 500,000 people. So the scale is completely different. And we are using genetics. So genetics obviously doesn't really explain a lot of variants of phenotype. So I think there are a lot of challenges. And now in our field, at least, there has been a lot of emphasis on, say, machine learning or artificial intelligence. And there are a lot of new techniques that are coming in, like a couple of months interval. So it's also quite challenging to actually keep up the work. For us, we might be okay with the techniques that we have been working on, but I mean, sometimes I even have to learn from my postdoc as to like what these new techniques are and how can they apply to our studies. So I think that's the interesting part in science.
If I may, I
Yes,
might
please.
share.
Yes, please.
I'm a faculty in computer science. I do a lot of deep learning, machine learning work. So I'm the I'm the not of officially, but I got the notice I will be the 2022 awardee based on develop a deep learning approach for aging cloud. Now here's the catch: I don't have any data because the award given to me just proposing a method without any result. So I propose the idea there, but I have zero data to work. So that's the funny thing about.
Right.
Yeah. So.
No, I think that's essentially what Dr. Zhao mentioned. I mean, for us, I mean, we always need to apply for grants from different sources. For example, the government grants that we often apply, you usually need to have preliminary data, and even though the universities might have provided you with the seed funding, probably it's just too little for you to do anything useful. So that's why, I mean, for the Healthy Longevity Award, I mean, they actually provide you with sort of reasonable lump sum of money for you to actually carry out to do any pilot studies. And if the studies actually showed what you hypothesized, and then that would actually provide you with the foundation to build on what you propose. And I think that's actually a very good way to help us to get the funding that we need to advance interventions related to not having longevity. Okay, so I think I have a question for myself from Dr. Zhou Zidong. Can I ask any new target genes or pathways have been identified which can be associated with metformin function? Yes, I think that's an interesting question because in the past, people thought that the AMPK pathway is the main pathway which metformin impacts longevity. But now, I mean, there are increasing evidence that there is both the AMPK and AMPK dependent and AMPK independent pathways. I think one of the key things that we are often concerned of with using genetics to infer the functionality of the drug or the proposed drug target is that different databases give you different information. So for example, if you look at the literature, they might have proposed some of the gene targets, but if you look at DrugBank, which is one of the major databases indicating the functionality of metformin, meaning that how it impacts disease outcomes, they provide another set of genetic variants or another set of gene region. So it's quite challenging. And for metformin, one of the other issue that we have to overcome is the phenotype, because we know that metformin is a hypoglycemic drug, meaning that it reduces blood glucose. But then, I mean, when we talk about glycemic traits, I mean, you can use glucose or you can use HbA1c, and there are increasing evidence that these are not exactly equivalent, although they are both used for diagnosis of diabetes. So I think there's still a lot of issues regarding how we use genetics to infer drugs effects. The other approach that might be more feasible is to look at the proteins themselves. Then you will be able to avoid the problem of using the proxy phenotypes to select your variants. But proteomic analysis is only starting to pick up. In the past, people focused more on genomics, but now proteomic analysis is something that becomes more popular. And if we have larger genome-wide associated studies on proteomics, then we might be able to identify more relevant variants related to these drug targets. And that essentially will be useful not only for metformin, but also other drugs which might have pleiotropic effects, for example, like statin or even the SGLT2 inhibitors, which seems to have quite a lot of protective effect, not only on diabetes outcomes, but also on, say, cardiovascular outcomes like heart failure and renal protections that have been shown in randomized controlled trials. So there are still a lot of things that we can play around with genetics. And I think nowadays for drug companies, genetic validation is something that they will also look at, because if they just simply run a trial, a phase 3 trial, exploring the relationship between drugs and outcomes sometimes is too risky and may cost a fortune to the companies. All right, any other final questions? We only have 3 minutes left.
Ryan.
Yes.
Could it be that drugs like metformin has potential to extend lifespan because they have many targets instead of just being very specific?
Yes, that's right. So that's why in our analysis, we actually identify multiple targets based on the literature. So for example, apart from the AMPK pathway, there are also other pathways which has been proposed. For example, let me just take it out. Right. So for example, apart from AMPK, there are also other pathways, for example, like GPD1 and things that I can't really spell off because they are abbreviated, for example, PSENEN. So these are additional gene regions which were thought to be related to metformin. I think the key thing with regards to this drug is that because the pathway is so unclear, so it's very difficult for us to really choose the relevant gene region to proxy the effect. So that's why one of the things that we might want to do is to, for example, first of all, run a randomized control trial to look and see what is the signal of metformin apart from its hypoglycemic property. So for example, if we found out that metformin actually impacts protein levels, for example, maybe it impacts like 30 proteins, then we can actually try to look and see which variant actually mimics this kind of pattern, and we just go back in reverse instead of just identifying the gene region first and look at that. Because if we're doing it in that way, then that could actually miss out maybe key gene region which is relevant to metformin action, but because of our poor understanding of its property, we might have missed that out. So there's still a lot of things, lots of issues or limitations with existing studies on metformin. But I think this method is sort of more established per se, for example, for lipid modifying medications or antihypertensives, because I think those variants seem to behave more properly compared to the targets of hypoglycemic medication. So that's why no one works on hypoglycemic medication. It's so difficult to work on. But yeah, I think that provides a niche anyway. All right, so I think that's up, and thank you very much for joining this session. Maybe I'll pass the floor back to Emma.
Yes, thank you all. You will be moved back into the main room. So thank you.
Thank you very much for the participation.
Bye.